or it could be liquid. So this is more convex, this is less convex, right? And if light is coming in, if this is where the retina is, and light is coming in from the room, when it passes through a more convex surface, it's going to cause the light waves to be distorted, or it's the refractory index, as you might have learned in physics. So the waves are going to be bent, and they will meet at a point on the retina, which is where we want them to be. On the other hand, if the lens is less convex, then this refractory index is going to be less, and the light waves won't bend as much. Okay. So, if I am looking at something close to my face, think about the distance between here, what I'm looking at, and the back of my retina. Not very far, right? Correct? So, in order to get this to focus on the back of my retina, I need the light waves to bend very sharply. So I want my lens to be very convex. I want the surface to be very curved. On the other hand, if I'm looking at something way up there by the elevator, I've got light waves coming all the way in, at least the ones that I can see, and there's a huge distance here between there and the back of my eye, so I don't need that bent quite so much. So I don't need the lens curved quite so much. Okay. Now, the action on the lens always seems to be a little bit opposite than you might think. So we're going to do a little demonstration. Let's pretend Sam is the lens. So you come over here. Okay. And then we'll do two guys. And Julie, and so you are going to be an object. You come over here. You are a muscle called the ciliary muscle. Your muscle is attached to her by little ligaments. Now, I've got two people up here. In fact, there's one ciliary muscle. It just goes all the way around. So this way I've demonstrated as if it's all the way around, okay? And everybody is holding on to the lens with these little suspensory ligaments. That's what they're called. They suspend the lens in the center. Okay. Keeping in mind that Sam is squishy. If I were to take Sam out of there and lay her on the table, she would naturally become very convex. If I were to take Sam, the lens, out, she would naturally become very, very curved, very convex, very bulgy. Okay. All right. So if I want her surface to be very curved for near vision, all I have to do is make this muscle contract. It's a sphincter muscle, you guys. Look what happens to their suspensory ligaments. They become loosened, correct? There's no tension put on the lens, so the lens can take on its natural shape. And that's because the muscle, which is a sphincter circular muscle, contracts and comes closer to the lens. Right? On the other hand, if I need the lens to be more or less convex, flatter, because I don't want the light waves to measure so much, bend so much, then what I'm going to ask this muscle to do is relax. So relax, relax, relax. And look what's happening. They're pulling on the lens. The suspensory ligaments are putting tension on the lens. And the lens is going to get flattened out. Can you imagine? Can you picture that? If you had a water balloon and could pull out on its perimeter, wouldn't it get flatter? That's what we're talking about. So in order to look at something close, we want that ciliary muscle to contract. If we want to look at something far away, we want the ciliary muscle to relax. Get it? Contract for close, relax for far away. When they contract for close, the ligaments get loose, the lens becomes convex. When they relax, the ligaments get taut. Don't say the ligaments contract, because they are not muscle, but they get tight, and the lens becomes less convex. You see it, you guys? And it's the oculomotor nerve number 3 that controls the ciliary muscle. Thank you. Okay.